This video is going to give you an overview of regression. The outline is as follows. We'll talk about how regression relates to classification. I'll describe least squares linear regression, and we'll talk about the limitations of that and deal with how we can handle nonlinear target functions for regression. And some of the methods we're going to talk about for accomplishing this are using neural networks, using basis functions, and SVM regression. So first off, what is regression? So if you look it up, you'll find a formal definition that says that regression is a measure of the relation between the mean value of one variable and the corresponding values of other variables, which is a bit of a mouthful, but that's more or less correct. So the idea is that when you do regression, your goal is to find the relationship and the trends between the input and the output variables, which is such a vague statement, and in fact, technically is more general than classification, right? Because technically, classification is also trying to find the mean value of one variable, which is a discrete variable, and corresponding values of other variables, the ones that are inside the input. So slightly less formally and colloquially, regression usually refers to continuous output. So while classification, where we talked about binary classification, where you're trying to just predict whether something is in some class or not in one class, and we talked about multi-class classification, where we have lots of different classes that we want to categorize our data into. Well, in regression, you're trying to predict a continuous value. So an example of where you might be interested in doing this is if you have some data that you have some value you're trying to predict. Maybe you're trying to figure out people's salaries, and all you have is some measure of how long people have been working at their particular job. So you might see something that looks like this, where the numbers on the scale don't mean anything, but it might look something like this, right? Where the more experience you have, the higher your salary is. That's the usual trend anyway. And you might want to try to predict that, right? Our goal is to look at data and learn a model that can predict that from the experience, predict the salary from the experience. And the way that people typically do something like this is they fit a line to the data. So maybe it would be this line. I don't actually know. I just drew that myself by hand. But you try to fit it aligns the data, and you say, okay, well, that's the function, and then all the points that are off of that line are just there's some noise that's been added to it, the data that causes them to not be precisely on that line. And this sort of linear regression model is very, very common. And usually the way people try to fit one of these lines is to do something called least squares linear regression. So the idea here is that we have a function that's going to predict the continuous output just by multiplying it by some coefficients. So both x and w are in Rd, so they're both d-dimensional vectors, and we just multiply we multiply all the dimensions of x by some dimensions of w, add them all up, and that's our prediction. And maybe we have a constant feature at the tacked onto the end of x. So maybe x is a bunch of variables and then just the one, or just just the numeral 1 at the end, which would then the last entry in w would act as a bias term. So another thing you can note here is that f of x outputs a scalar. It outputs just a continuous valued, real valued number. And at the same time, the thing that we're actually going to try to predict, the thing that's going to be in our training set that we're targeting, which we're going to call y, is also just a single scalar per example. So for each example, we're going to have a d-dimensional vector. We're going to predict a one-dimensional continuous value, and we're going to try to match another one-dimensional continuous value that was given to us by the real data set. And then we're going to do all that with a d-dimensional w vector. So the training objective is as follows, and this is why it's called least squares linear regression, because we are trying to minimize the squared difference between what we predicted with our f function and the true y's. And we're going to sum them all up for all the data, and maybe we divide, in this case I didn't divide by n, but sometimes you divide by n, so you're trying to minimize the average least squares or the mean squared error. And a lot of times we'll want to regularize this, right? We don't, just like with classification, we don't want to overfit the data. So we also want to add some term like this squared norm that trades off between model complexity and fitting the data perfectly. So the two pieces of this objective function are a squared loss term and a regularizer. And this is the easier to think about form, at least for me, but it's also useful when we do some derivations to write this down in a matrix form. So here's the matrix form. So now f of x is not just going to take one data point as input, but instead it's going to take a matrix of data points where each column is an example, and it's going to output a vector of predicted values. So now y is going to be a vector, f of x outputs a vector, x is a matrix, and w is still that d-dimensional vector. Okay, and then the objective function we would optimize if we wanted to, if we write things in this matrix form, is the following. So this j function is a function of w, and it's going to be it's this inner product of the difference between the score that we predict and the true y's. And the score that we predict is x transpose w. And then we take all that and take the inner product with itself, which is equivalent to summing the squares of all the entries in that vector, right, which is the same thing as upstairs in the original form. Okay, and then we also add the regularizer. Okay, so from this we can do some manipulation to try to figure out how to solve this optimization. So we want to find the minimum of j, and the first thing we should do is we should just try to distribute some terms to write things out as explicitly as possible. So we can use the FOIL method to break apart the inner product here, and we get we get a quadratic term which is w transpose x transpose times w. Then we get this, I guess you can think of it as a linear term, so it's y transpose x transpose times w. Then we have y multiplied by itself, which doesn't really affect our optimization because it doesn't have anything to do with w. And then we have the regularizer term. So this is pretty easy to work with now because we can just take the gradient with respect to w. And the gradient with respect to w is as follows, right? So we have the x transpose times w, and then the linear coefficients, all transpose. So now it's x transpose y, plus lambda w, just like we saw in all of our other things where we were using this squared norm regularizer. So with this, you could do one of two things, right? You can either just use the gradient and numerically optimize by sliding down the direction of steepest descent, or in this case, it turns out we can actually just solve for when this is 0, with a minor caveat. So for now, I'll just show you that we can solve it, and I'll tell you what the caveat is at the end. So yeah, if we want to solve for this where this is 0, it's actually this is really easy. You just group some terms together, and I think the trickiest part of all this is just figuring out how that lambda w fits into the matrix vector product on the left, and the way that it fits in is that it becomes lambda times the identity matrix all times w. So you get x transpose plus lambda times the identity, all of that multiplied by w equals this other thing that's a constant, x transpose times y. And then in order to actually solve for w, we just multiply both sides by that coefficient matrix inverted, and you get this. So this is a closed form solution. So we can solve the least squares problem just by computing this matrix inverse, multiplying it by the data matrix and the label vector. But a couple things can go wrong, right? So what we have to consider is that first off, this requires doing a matrix inverse. So there are situations where the matrix may not be invertible. And then moreover, we have to consider what this matrix is. So what is this x transpose matrix? And here's a hint, it's not the kernel matrix. It looks a lot like the kernel matrix, but remember the way we wrote things in looking at the SVM, we used columns to represent the data examples, and we had written x transpose x as the linear kernel gram matrix. So in this case, it's XX transpose. So what's the size of XX transpose? It will be, D by D. So if D is huge, this could be a problem. But in most cases, D is reasonable, so we can handle a D by D matrix. Okay, so this is the closed form solution to least squares, and this is the standard way most people study least squares, and that's basically the end of the story for most people. But for us, we're going to care about things being a little bit more general than what we've written here. And in order to make things more general, we're going to go back to the original form of the objective function up at the top. So we'll move that down. That's what we're going to care about now, the original form of the objective function. And let's look at the pieces of the objective. So we had something that's the squared error. So it's the difference between the prediction and the true labels, or not the labels, the true y values, all squared and divided by 2, and then a regularizer. So we can break this apart and generalize a bit more by calling this the loss function. So if we say the loss function is 1/2 the difference between a prediction and the true value, all squared, then we can just plug that in and drop that in for in a general equation that just uses the loss function. And now that we've written the loss function like this, we can actually write down the derivative of the loss function, which is just z minus y for the input z, right? So if z is the input to the squared loss term, then we just subtract z from its target value, and that's our derivative. And that comes in handy when we want to take the gradient of the objective function with respect to w. So the gradient of the objective function with respect to w is the gradient of the first term with respect to w, and the gradient of the second term with respect to w. And that's where, if we take the gradient of the loss term with respect to w, we have to apply the chain rule. And this should start to look somewhat familiar. So we have the general form where we have the chain rule, so we have the derivative of the loss function all times the gradient with respect to the prediction. So the gradient of f. And now if we look at this particular f that we're working with, this f which is just the linear, w times x, the gradient of f with respect to w is just x. So from here we can see this general form equation for the gradient is written with respect to the derivative of L and the gradient of f, which we can plug in these things that we wrote at the top for the squared loss and for the linear f, and it works out. But we could also imagine using this with any other loss or any other f function. So that brings us to the idea of nonlinear regression. So one of my pet peeves that I see reasonably often in science and popular press news reporting that attempts to be scientific is that a lot of times people will look at some data and it looks super noisy, and then they fit some linear trend to that data. And in many cases, I get annoyed because it's obviously not linear, and it's mostly noise. But now sometimes it's not just that it's too noisy for there to be a real trend there. Sometimes it's actually that you can see there's some curvature in the trends that the linear fit is not going to capture. So our goal here for the next couple slides is to talk about how do we take some of the concepts that we've learned so far and use them to do regression in a way that can capture nonlinear trends. So the first approach we'll talk about is to use neural networks for regression. And this is where, that general form of the gradient I wrote a couple slides ago is going to come back. So here we have that general form. It's written with respect to L, or rather the derivative of L, and the gradient of f. So it's really, it's really simple actually. What we're going to do is all we have to do is use a neural network for f, and then when we go to compute that gradient of f, we just use backpropagation the same way we did with classification. The only difference is when we did classification with neural networks, we were using log likelihood as the loss, and here we're going to want to use something like the squared loss. So the error that we were propagating back in backpropagation, again, instead of using log likelihood, we would use the squared loss that we talked about earlier. So this part changes a little bit compared to what we had for the gradient of the outer, the final output layer of a neural network. But then all the intermediate, middle layer stuff is all the same. So that's one approach. And then another approach is also very analogous to something we saw, which is to use basis functions. So the idea is to do linear regression on transformed features. Right, so instead of writing f of x as w times x, we're going to say that f of x is w times phi of x, right? Where phi is something that takes x as input and transforms it into another dimensional space. So we could do the polynomial thing that we did for the SVM, and we could say we take x squared, x cubed, x to the fourth, etc., and we use that as our phi, and then we end up with another closed form W solution that looks very similar to what we had before, except now we're using these transformed features instead of x itself. So this is all fine, and this works very well in practice. A lot of times you can just look at your data and decide, well, that looks kind of quadratic, so I should square something, square the values and use those. Or sometimes it looks like you need to take a log of some values to make them more linear looking. But the problem is that the more you tack on to this feature transform phi, the larger that phi vector is, the more expensive it is to do this computation, because you have to compute a d by d matrix, where d now is the dimensionality of the phi vector, not of x. So the problem with this approach is that you need to explicitly compute feature functions. Now, like I said, in practice this generally works pretty well. But if you did want to use a huge number of feature functions, then you're going to want to go to some place where you can use the kernel trick. And remember, you can't use the kernel trick here because this is not a kernel. It's not a gram matrix. It's phi transpose, not phi transpose phi. So the last idea we're going to talk about is SVM regression, so support vector machine regression. And the idea behind SVM regression is a little bit different than least squares, in that instead of trying to minimize the error from every point to the line that we're trying to learn, we're going to try to build. We construct what is essentially a tube around the line that we want to fit all of the data into. So what I drew here doesn't do the job perfectly because some points are outside of this pink tube, but you could, maybe this is because of regularization. But the idea is that what we want to do is we want to fit all of our data inside this tube and make it as narrow as we can make it. And the optimization for solving SVM regression in the primal form is this as follows. So you have you minimize the squared the squared norm, or the weight vector multiplied by itself, subject to a certain constraint. So the constraints will look kind of familiar, and you can probably reason through what exactly they're doing. So you want to make sure that for every data point, w times x minus y is less than epsilon. And so let's think about what these are. So w times x is our prediction. That's what we're predicting. That should be something like the red line on the picture. And y is the true value. Y is the actual value that we're trying to predict. So we want that to be less than epsilon. So that captures one side of this tube idea, and then we need another constraint that goes on the other side that says that y minus w times x is less than epsilon. And if both of these constraints are satisfied, then every single point is within epsilon of the center line, the center red line. And it takes a bit of staring at this and thinking about it to see how this relates to the classification SVM that we worked with. And there's a few intuitions you can pull from thinking like that. And one of them is that you can think of this as like a reverse SVM. Right? Remember, in the SVM for classification, our goal was to make sure all the points were outside of the margin. Right? We wanted to classify every single point by some margin so that no points were within that neutral zone. Okay, and now instead what we want is to stick all the points into that neutral zone. So it's very, very similar, but the constraints kind of play an opposite role than they did in classification. But despite the fact that they play an opposite role, they look very, very similar. The mathematical form of these constraints is very similar, and that means that you can do almost everything you can do with the primal classification SVM with this regression objective function. So you can do things like add slack variables, which we would have needed in this picture I drew here because some of these points are outside the tube. You can take the dual with taking writing the Lagrangian, adding the KKT multipliers and solving for the KKT conditions, and you can kernelize the dual that you end up deriving, and you end up with the kernel SVM regression technique, which, just like classification, or analogously to classification, is just a linear regression, but in a mapped feature space. And that mapped feature space can be arbitrarily complex, right? It can be something like the RBF, where the feature space that you map to is infinite dimensional, but you can work with it but just by using kernels. So that's it. So to summarize, I talked about how regression relates to classification, and you can think of regression as just classifying or outputting continuous values instead of discrete values. I talked about least squares as the objective function and a linear predictor, and how that leads to a closed form solution for the linear coefficients. And then we talked about three different methods for nonlinear regression. The first is using neural networks, so having multiple layers instead of just one layer, and add squashing functions that will add nonlinearities. The second was to use basis functions, so to transform your input data into some other space, other representation, and then do a linear classifier in that other representation. And then SVM regression, which in the primal already takes a different view on the goal of regression, but in the dual allows you to use the kernel trick to implicitly compute very complex basis functions.